For Teardown today, we have a Vision Research Phantom V4.1 high-speed camera. This is a pretty old camera. This was released in 2001, I believe. There's a 512 by 512 pixel image sensor running at 1000 frames per second and lower resolutions at higher frame rates. This is back in the days when FireWire was very common, so this has dual FireWire ports. Along with a power and triggers connector and a display video output. As far as I know, what the idea with this, the FireWire dual FireWire ports is, you would connect your computer to one, and then you would daisy chain multiple cameras to download video. And of course, Ethernet has completely replaced this now. I picked this up on eBay for 150 bucks. It didn't come with any cables, unfortunately, or the control software, so at the moment I'm unable to use it. If anyone knows of the cables, they can check the pinouts for me. Although that's something I can probably figure out just by reverse engineering, but if anyone has the control software for the PC especially, that would be extremely useful to get this camera running. It looks like in an older version of this camera they had 3 FireWire ports, judging by this hole. This is just some sort of rubber cover. I guess they didn't like how the camera looked. It does kind of look a bit weird, so they added that rubber cover. Yeah, the previous version had a 3rd FireWire port as well. I'm not sure exactly what that was used for. Really solidly built, weighs about 2 kilograms, all aluminum construction. I'm guessing extrusion plus machined ends. The tripod and other mounts have these helicoil, I think they're called, inserts to make the connection stronger into the aluminum. Anyway, let's open this up and see if we can figure out where to connect power, see if we can get it to do anything. I contacted Vision Research about getting the control software for this. I don't know if it's just because it's near Christmas right now, but they haven't gotten back to me. And hopefully in the new year, or again, if someone can provide a copy of the software, that would be awesome. Now, I'm sure it's probably going to operate only on Windows 98 or XP, given how old this is, but certainly better than nothing. I posted some links to the spec sheets in the video description if you want to go have a look at them. Seems a pretty typical high-speed camera from the era. Apparently this won an award in 2000 when the V4.0 was released for some sort of R&D 100 product of the year. It really was quite revolutionary. If you've seen the other systems I've torn down, they're huge things with a big processor box and then a camera head, and this is all self-contained in one unit that just needed a computer for operation. So let's see. Oh, there we go. Oh yeah, that's really nice machined aluminum there. The gasket. Rubber gasket seal. Okay, so we have another couple of Allen key things here and a few little switches. Oh, here it says something here. Sandia National Laboratories, New Mexico. And serial number VR1071169 V4M is monochrome. Ooh, it has the 1 gig memory option, it seems. Yeah, the standard version of this had 256 megs of memory, which only records for 1 second. So this apparently will record for 4 seconds. So now how do we get this apart? Looks like we have to take these screws out. Let's see if we can, if the front is any more use. Okay, so there are different lengths, so I can try that. Okay. Oh, we have lots of FFC goodness there. Okay, let's see if we can. We got lots of. Oh wow, 1, 2, 3, 4, 5 boards in there. Sort of a card cage arrangement. These FFCs are all glued, so let me see if I can get these out. It looks like they are not glued on this side, so I can disconnect that. Also just going to number which ones these go so we don't forget which boards they go to. Okay, this seems to be the right tool for this particular job. There we go. Oops, things loose. Turn around. Okay, and there we go. So it looks like there's screws holding the two sides of the case together. So we're going to have to take these strips off. Yeah, that's not too difficult. Probably going to have to get some new double-sided tape to put these back on later. Okay, let's see if this comes apart now. Oh yeah, that's pretty easy. Ooh, what do we have here? Crucial memory from Crucial, huh? This is not any standard memory format I've ever seen, though. It's like a double height SODIMM. That's really interesting, huh? Anything in here? Huh. Oh yeah, bit of that's really sticky, super sticky. Is it a thermal pad? Doesn't seem very cold. Yeah, it seems to be just a piece of foam to hold the memory in. Come to think of it, this foam rubber stuff, it's definitely not thermally conductive, at least not significantly, but it's probably something for vibration absorption, because all the boards are held at the end of the card cage, but not in the middle, so this probably helps stop the boards from vibrating around too much, especially if you vibrated the camera enclosure at the resonant frequency of the boards to prevent oscillations from coming. And oh wow, this whole thing appears to be machined aluminum. Yeah, these things seem to have been machined out of solid blocks. You can see little, looks like marks from cutting head chatter there. Yeah, these things, cost was no object. These things were built up to a spec, not down to a price. Anyway, so we have 5 boards here. This one seems to be a power supply board. Wow, look at those huge surface mount DC to DC converters. Let's see, what do we have here? We have 1836 volts in, 5 volts 6 watt, 3.3 volts 6 watt, 5 volts 6 watt, and there's some other ones. We'll have to pull the board out farther. Yeah, let's get these boards out of here. I'm hoping, yeah, that looks like the entire module will just lift out. And there's another thermal pad or something here. I'm just going to mark, this is the bottom and that's the top. And are these symmetrical? They appear to be identical. I should probably check which one is the front, although it doesn't actually seem to matter. Let's mark that. I think that was the right way around. I'll check on the video if that was actually right. Although, yeah, these appear to be completely symmetrical, so it doesn't really matter which way you assemble them. Yeah, it's nice. You can just machine one thing. That one thing is used for both sides. Okay, looks like there's just some long, very long screws driven through this. Yep, then these should come off. So I have to figure out how to get the other end off, because there's a lot of connectors on here. I'm thinking some of these are glued, so that'll have to be, just figured how to remove that. So let's see how this is going to come apart. It looks like, yeah, it's hitting a resistor there, so we're going to have to take it off from the back here. Okay, that one's free. Now I can just get the Allen wrench out. Okay, now the card cage should be able to come apart. It looks like this one has just one board-to-board connector. This one will have to, this one must be the I/O interface, has the FireWire on it, so these must be trigger signals. Come on, stupid hot snot. Okay, now you have to carefully prise those apart. The whole stack is just done with board-to-board interconnects. There we go. This is again hot snotted onto the board. Have to be careful not to rip the ribbon cable out of this. Might get that one from the other side. Let's see. There we go. Right. And these look like two identical boards for the analog to digital converters. I should probably, I've already labeled the order of these boards so we can put them back together in the same order. Starting off with the power supply board, not too much to see here other than these odd DC to DC converter modules in these giant surface mount packages. The pin pitch is something like 6 or 8 millimeters. There's 3 5-volt modules, these ones, and 3 3.3 volt modules, totaling about almost 36 watts total. And either they're doing plus or minus rails, or they need additional modules for more power, or they're doing separate rails for noise separation. And on the other side, there's not huge much else. A few small DC to DCs. This is the power input over here. There's some fuses, filter caps. This is the power output to the image sensor board. Some filtering, inductors for filtering. Probably some other DC to DC converters. These are labeled macro DENs made by Ericsson. Part numbers PKF2611 for the 5 volt and PKF2610A for the 3.3 volt modules. This board is labeled as the Phantom V4 interface board. This board has different date code than the others. There's a sticker here that says April 2003. Some of the chips date from around 02, 01, around that time. So it looks like about when the camera was built, unless it was potentially upgraded at that time. We have two big things on this are Xilinx FPGAs, XC4010s. These are 400 logic block. They also have about a little bit over a K of RAM. We have a 27 megahertz clock, a 24.576 meg. This is an ADV7177. That's a PAL NTSC video encoder, no doubt for the viewfinder and the video outputs. There's a 8K by 9 FIFO and another 1K by 9 FIFO. It's an IDT72V251 and a Cypress CY7C4221, which also happens to be a whole bunch of those on some of the other boards as well. This is another Cypress. It's probably a RAM. On the other side, there's not too much. There's a TI FireWire. This is a 3-port FireWire physical layer controller. Clearly, they used to have a room for one, and it looks like they've also pinned it out to another connector. Looks like for an optional thing, probably on one of the circular connectors. This is a Philips PDI 1394L. This is a FireWire triple port AV link controller, and this is used for apparently it contains hardware to packetize video data into standard video packets. I wonder if they're using that for an actual FireWire video, like DV compliant video on this, or if it's just something just to get data onto it. I'm suspecting it's just sending raw data over these for their control software. And there's just a flash memory that's probably either for storing the fixed pattern noise of the image sensor, or more likely just configuration memory for the FPGAs. This board is labeled the Phantom V4 CPU timing board. This one, the silkscreen has a date of 2000 on it, whereas the previous board, the interface board we were looking at before, has a date of 2002. So I wonder if this is, they just keep using these older boards because they didn't need a change, or it's just that the other board was upgraded. Anyway, on this we have a couple of Xilinx FPGAs, same one as on the other boards, 400 logic elements. This is a CPLD, 144 macro cell. This one seems to be connected over to this board-to-board connector that goes over to the image sensor boards, and based on the timing designation, this is probably the image sensor timing generator. Just above this is room for a couple of clocks. This one is 80 megahertz. On the other side, we have a Hitachi Renesas now, HD64F7045. That's a 32-bit CPU running at 28 megahertz, I believe. That's connected to some flash memory. And then on the other side of the board, there's more flash memory, some couple of different package types. Not too much else on this. There's an RTC up here. That's probably a reset button. These might be debug ports because these are not accessible when the camera is put together. On the other side, there's a little polyfuse probably, and there's a bunch of, these are 8-bit tri-statable bus drivers. These are likely used to connect things on this board like the CPU bus and the FPGA onto the main acquisition RAM bus to be able to read and write to that. And this board also seems to have all of the trigger, I believe all of the I/O, like the timing in and out, trigger in and out, and sync signals come on this cable. So those also probably goes through. There's probably some input protection on here somewhere, and these are probably also brought out to these other connectors. I see some of the pins from this one go over to these as well. I'm not sure what the layer count on these is. You can definitely see over here some tracks on the next layer down. That's not something you usually do today because of high speeds. You'd have a ground plane in between the signal tracks, but on these older boards that don't run so fast, it wasn't anywhere near as critical, and you can see they're doing the same thing here. So this is probably, I'm thinking, a 6-layer board, although possibly as few as 4. On the Phantom V4 memory board, we have a large SODIMM RAM module. As far as there's very little information on this. Of course, this is completely obsolete, but as far as I can tell, this is a 512 megabyte PC100 SODIMM. This is single data rate DRAM. As I said before, I've never seen a module this big. It's obviously a standard product based on the labeling, but it must be something uncommon, like for a very large memory expansion for laptops, because back when this thing was made, 512 megs was a lot of memory for a computer. This board seems to take in the analog signals from the image sensor, 8 channels on this connector, and on the other side of the board we have 8 analog to digital converters. These are AD9203. These are 10-bit 40 megasample per second, and looks like each one of those has its own FIFO memory. Those are those CY7C4221. Those are 9-bit by 1. 1024 by 1K. It's odd they're using 9-bit. I would figure they would either use the full resolution of the ADCs, 10-bit, or they take it down to 8. Because, as far as I know, this RAM is 64-bit, judged by the 64 numbers, so I'm thinking that they are just throwing away the extra 2 bits of the ADC resolution and only saving 8-bit data to the memory. It looks like they hadn't really intended to put longer sticks like this in, judging by the silk screen you can see in there, and the fact that the module is actually, get a light in here, actually hitting components on the board. They've had to sort of glue it in. It's kind of a bit of a wonky way of doing it, because this camera is supposedly rated for high G, up to 100 G for 10 milliseconds, I believe. That's kind of, I'm not sure. I guess they've tested it and this is good enough, but yeah, I kind of want to see a bit better, like something, at least some sort of clip to hold the memory in so it can't fall out. Elsewhere we have more of these octal bus buffers. It appears that the data from the image sensor is not being routed through an FPGA. There's no FPGAs on this thing big enough to do that, so the data from all of these FIFOs is being sent straight onto the memory bus. And this small FPGA, or this is a CPLD, this was a, what was this? It was a, I think 108 macrocell CPLD. This must take care of the memory timing and interfacing the memory to other boards over these connectors. Of course, because there's 2 of these boards, that indicates the image sensor has 16 analog channels total. And just based on the pixel rate of this, they're probably running the image sensor somewhere on the order of a 20 megahertz clock rate. There was a 28 megahertz crystal on one of these boards, so I'm betting that is going to be the image sensor clock. We'll see if we can get the image sensor board out here. I'm hoping we won't mess up the alignment, although I suspect it's going to be set by the thickness of washers, for example. Okay, I suspect this whole thing is going to come out as one module, or is it? Have they hot snotted it into place is the question. There's probably a board-to-board connector between these two, yeah. Okay, oh wow, look at that sensor. Oh. That reminds me of CPUs from back in the day, wow. All for such a little image sensor size, wow. Anyway, save that goodness for later. What do we have on here? It looks like, let's get that closer in. We have a bunch of Max 603 and some, I don't recognize that manufacturer, little E with a symbol. Let me look up what those are. Anyway, this is labeled as the Phantom V4 driver board, Rev C. Those are probably analog drivers for the image sensor. So the Max 603s are just LDO voltage regulators, so there's 6 of them, 6 different rails for this. And these parts turn out to be EL7514, they call them pin drivers. They're basically 4 amp high current buffers that can operate at weird voltages. This is probably required by the image sensor for all the different bias and clocking and things that have to drive the pixel array. Also on this board we see the one bodge wire that I've seen in this entire product. And there's a whole bunch of pots and I don't dare touch because I have no idea how to reset them. And a few test points probably for setting different voltages. These probably control the voltages that these regulators run at. And there's also a bit of 7400 logic. So I'm not quite sure how we get the board out of this. These Allen screws seem to just clamp the lens mount in so you can move it forward and back for backfocal adjustment. These don't appear to be removable standoffs. But it's sort of hard to see. It looks like they've... It's very hard to see in there, but it looks like they've... the bastards have glued the bottom standoff in, huh? I kind of still want to see the image sensor. I'm going to try unscrewing these. Let's see. Oh, yeah, that looks like that is coming. Let's get these cables off. Let's label those. That is 2. That's 1. Oh, that's glued too. Not very well, of course. Anyway, let's see if I'll try to get these off. Okay, that wasn't too difficult. Now, oh, yep, that's free. Here we go. Oh, look at that. And wait a minute. That's a lot bigger, huh? Okay, so they're using the same image sensor from multiple cameras. That looks like a 1024 by 1024 image sensor, huh? I guess it was cheaper than making different chips. Interesting. I wonder if it has more readouts. This one has 16 channels readout. I wonder if this bigger image sensor actually supports more. That is really interesting, and it's just sort of masked off. That's why that mask is there. I was wondering why the mask looked sort of off-center on the chip, and it's because the actual active image area is bigger. Huh. And in here, yeah, they've glued these standoffs in. Looks like they to get the chip to fit in this corner, they had to machine it off after they put it in. Huh. Kind of a bodge there. As far as I know, this image sensor is made by Fill Factory, was the original company name. Then it got bought by Cypress. Then that got bought by ON Semiconductor. Huh. Let's see, what are these little chips here? National Semiconductor 1M02AB. Let me figure out what those are. Anyway, this says the PH4SN Phantom 4 SN Rev C. These parts turn out to be CLC114 quad low power video buffers. These are to have a 200 megahertz bandwidth and are probably used to amplify the low level signals or buffer the low or high impedance signals coming out of the image sensor. But yeah, this is odd. It's odd that they would design such a large image sensor and then only use the small active region. I guess it's because a huge amount of money goes into making custom parts like this, so they probably just decided to make one part and use it throughout their range of cameras. Although when this was initially released, this was the highest resolution camera they offered, although they soon later released the Phantom V5, which is twice the resolution, 1024 by 1024, which I believe this sensor is, and runs at 1000 frames per second. So I'm thinking that this image sensor is capable of 1 megapixel at 1000 frames per second, and they're just using it at this lower frame rate for this smaller camera. What I'm thinking they're doing, let me zoom into the image sensor there. Unfortunately, I don't have that microscope I was using before, so we can't get such nice images, but I'll do what I can. Here's pretty much the best close-up of the chip I can get. Unfortunately, yeah, it's nowhere near as good as that microscope. And it's really hard to see on this image. You probably won't be able to see it, but there's a little faint line running right down the center of the chip, and I think that's where basically the chip is divided into two sectors, the top and bottom, and there's a mirror of the readout circuitry. Basically on the bottom of this and the top of this is readout circuitry, some number of channels. I'm guessing there might be 32 analog channels on each on the top and the bottom to get the full the Phantom V5's rate of 1000 frames per second at 1024 by 1024. And they're just using only 16 of the 32 channels on this one side, and only using the bottom half of the image sensor to do that. I guess it makes sense when you spend a huge amount of money making a custom chip. It's funny they have the foresight to make a higher resolution chip like this rather than starting out with a lower one. The only marking on the chip is this WAS7 or WA or W something 3.7-4. No, there might be a marking if it might be in the underside in the center, but we can't obviously see that. I'm not going to try to pull this out of the socket. And based on what I can find in the specs, the pixel pitch is 20 microns on this, which is quite large, way larger than current cameras, like cell phone cameras, which are only usually around 1 micron, and even DSLRs are 3 to 5 microns or so. Clearly the design of this wasn't an afterthought. I mean, this housing is clearly designed for this larger image sensor, although they've had to machine off that side there, but it clearly was thought out. It wasn't just an afterthought that they just, we'll throw in a larger image sensor. That pretty much completes the teardown. It's time to put this thing back together and try to get it running. at the very least, we can figure out, the power looks pretty simple. It seems to be just these two, the red and black wires on this. So let's put it back together and connect power up and see if we can get it to power up and maybe get a video signal out of one of these pins. I have checked and double checked and triple checked my connections here, and they're connected up to the power input properly. So let's give this a go. Okay, drawing 0.5 amps at the rated 28 volts. We got some lights. That's a good sign. The current draw increased from 0.45 to 0.55, I guess, after the FPGA is booted. Okay, that all seems to be running. I'm going to probe around these connectors, see if we can find the video output. There should be an NTSC video output signal. That looks like sort of like something. Let's get it down to where we actually might see a full frame. Quite a lot of noise on that. I have an inkling that the ground, power ground, might be isolated from, oh, there's something. What's that? Definitely some sort of strobe signal. 7.35 kilohertz. We have this at 100 hertz, almost precisely 100 hertz. That's the closest thing that we have seen to a video signal so far. Let's take a look at in more detail at that. Shine some light into the front. Oh, yep. That is definitely the video signal. So let's get an NTSC monitor. Okay, this seems to be working. We have a live image on the display here. It looks like it's currently set to a small, a low resolution and very high frame rate because the sensitivity is very low. I found a strobe output on the on one of the pins here. If you look up on the scope, that is coming out to what are we getting? 7.35 kilohertz. So I think that's the frame rate that it's operating at right now. It's operating at an odd, it's like down in the corner, like this is the active area, which is not anywhere near centered. Like that's centered right there. This is in the corner, so definitely need to get the copy of the control software to operate this, but yeah, it does seem to be fully operational. One other thing I noticed when moving this around is the TV display. You probably won't be able to see this if you're watching at 30 frames a second, but the TV display only updates at 30 frames per second. I would have expected it to update at 60. I don't really see why any reason you shouldn't be able to do that, unless it has to do with the fields versus frames for NTSC. I couldn't find any video coming out of this connector, so I'm thinking, also based on how the connections are done inside, that this is FireWire. They just moved it off from this port off to a much more rugged connector, so if you wanted to operate this in a high-G environment, you don't have to worry about your FireWire connector coming out. Anyway, last thing to do is to see what this comes up as when you connect it up to the PC. FireWire going in. Found something, obviously no drivers found. Unidentified device. Now, what did that come up as? Probably one of these unknown devices. Yep, something on the 1394, and the other one is, that's something else in the PC. So, hardware, let's see. Does it tell us anything at all interesting? Doesn't look like it. Yeah, so we're going to need the FireWire driver and the software for this camera. So yeah, if anyone has a copy or has access to a copy of the software for this, for Phantom V4 or anything, perhaps even later, although I know at some point they removed support for these older cameras, but if someone has access to the software and drivers for this, please send me a private message on Facebook, on not Facebook, on YouTube, or send me an email. My email is in the video description. Yeah, it would be great to get this camera fully operational. That was a really interesting teardown. This is a really cool piece of late 90s / early 2000s technology. Anyway, yeah, if anyone has any leads on getting the software for this, or knows someone at Vision Research to contact who would be particularly helpful, please let me know. Anyway, hope you found that video interesting. Thanks for watching.